So this video will also be about subgroups. We are going to look at this two-step subgroup test. So let G be a group and H a non-empty subset of G. Then H is a subgroup of G if AB is in H, whenever A and B are in H, so it is closed under multiplication, and the inverse of A is in H whenever A in H, closed under inverse. So first we gain some intuition here. So we have a group G and H is a non-empty subset, okay, of G. G is a subgroup of G if AB, so we pick A and A is in H, we pick B, B is in H. I don't like this H here, I need to put it here, okay. So A is in H, B is in H, and the set is closed under multiplication. A times B is in H too. And the inverse of A, for any A in H, is also in H, so it's closed under inverse. So proof. By the one-step subgroup test, we can say that if A, B are in H, if A, B are in H, implies that A times inverse is in H. If this happens, H is a subgroup, okay? So we suppose that A and B are in H, okay? So H is closed under inverse, right? So since H is closed under inverse, B1 will also be in H, right? So if this is true, A times the inverse is in H, right? By closure under multiplication, because A and B are in H. So the inverse, whenever A, the inverse is also in H, okay? So in this case the B inverse will be in H. But A and B in H, they have to be closed under multiplication. So A times the inverse is also closed under multiplication. Okay, so by the one-step subgroup test, H is a subgroup of G. And this concludes the proof. This theorem, well, it's a theorem only for finite subgroup tests. Okay, for finite subgroups. Okay, and it is a finite subgroup test. Let H be a non-empty finite subset of a group G. Then H is a subgroup of G if H is closed under the operation G. It looks very simple, and it is very simple, and it is very nice too. So we are going to take the proof now. Okay, so we just saw the two-step subgroup test, right? I'm just going to remind you the two-step subgroup test. The two-step subgroup test says let G be a group and H a non-empty subset of G. H is a subgroup of G if AB is in H, right? Whenever A and B is in H, so it is closed under multiplication, and the inverse is also in H whenever A is in H. Okay, so if we look at the two-step subgroup test, okay, we only need to prove that A inverse is in H when A is in H. Okay, we just need to prove this. Okay, let us take A equals the identity. Okay, if A equals the identity, well, if A equals the identity, the inverse equals A, and it's done. Now, if A is different from the identity, we are going to consider the sequences A squared, A cubed, etc. But H H is finite, right? H is finite, and closure implies that all positive powers of A are in H, right? So A, A2, A3, all positive powers are in H. But, this is very important, but not all of these elements are distinct. Do not forget that H is finite, okay? So you can't go on and on, okay? You will get to a point where the elements will repeat. Okay, let us say that A to the power of I equals A to the power of J, and I greater than J. Okay, so they will be both positive, but I will be greater than J. So this can be 3 and this can be 2, for instance. Okay. Okay, so Ij implies that A to the power of I A to the power of I minus J equals, it has to be equal to the identity. Yes, because A to the power of I equals A to the power of J. Okay, so I minus J equals the identity. Okay, so if but A the element A is not the identity, right? Okay, and since I greater than j, I minus j, it has to be greater than 1, right? So a to the power of I minus j equals a times a to the power of I minus j minus 1. And this one, of course, it will be the identity. So a to the power of I minus j minus 1 so it will be, of course, equal to a, the inverse of a. Okay, but I minus j minus 1 is greater than 1. So this implies that a to the power of I minus j minus 1 is in H. Okay, and we are done. And this concludes the theorem. So our theorem is the finite subgroup test. Let H be a non-empty finite subset of a group G. Then H is a subgroup of G if H is closed under the operation G. Okay, so for the proof we are going to use the two-step subgroup test. Okay, so this means that we only need to prove that the inverse of A is in H. Okay, that if A is in H, the inverse of A is in H. Okay, first step, if A is the identity, okay, first case, we are going to see case by case. Okay, if A is the identity, the inverse of A is A, and we are done, right? Because the inverse is in H, so it would be proved that H is a subgroup. So if now second possibility, case by case, second case, A is not the identity. Okay, so we pick A, then we do the operation again with A, and the operation again with A. Okay, so we will be getting A here. After this operation we'll be getting A squared, then A to the power of 3, etc. But as I said, this can't go on because H is finite, right? H is finite. This can't go on and on. It will stop somewhere. It will stop. Okay, but the fact is that all these members or all these elements will be in H. Okay, because H is finite, but closure. Okay, but is closed. So since H is finite, okay, and closure guarantees that all these elements are in H, since H is finite, we will get to a point, there will be a to the power of something here that will be equal to the power of something here. you see, and so we don't know which element here, which power x here will be equal to which power here. We don't know. So we say there will be a positive I, a to the power of I, that will be equal to a to the power of g. It can be 2 and 5 or anything, okay? So we are calling this I because this will be this one, okay? This one we are going to call it I, and it will be bigger than, for instance, this one, okay? So this one will be our j, okay? And there will be a point where this one will be without loss of generality, no. Taking an arbitrary example, okay? It could be with 3, okay? We simply don't know. So, okay, so there will be a moment where I will equal j, where I is greater than j, of course. Now, I've noticed too that this implication here is a bit confusing. So, let us imagine that AI that is equal to AJ, where I is equal to J. Let us, for instance, take this as if it was 5, for instance. So it means that A5 equals, let us take 2, for instance, okay, equals A2. Okay, so A5 equals A2. This implies that so what is 5 minus 2? 5 minus 2 will be 3. Okay, and since this is the element that will start repeating, okay, it means that so since 5 equals 2 in a way, right, this power of 5 here equals 2, it means that a to the power of 5 minus 2, it's a to the power of 3. So the next one, you see, it will be the identity, okay, because this is the one that gets to a point where it repeats itself. So the next one will be the identity. So a to the power of 5 minus 2 will be equal to a to the power of 3, and that will be the identity, right? So a to the power of I minus j, and these ones are the repeating ones. Do not forget they both are equal, okay? Or a, since they are equal, a to the power of 0 is 1 if it is more convenient for you to think that way, but I don't like that. Okay. So the next element, next j, so this will be a to the power of j plus 1, right? Okay, and I minus j cannot be 0. Okay, if I minus j and cannot be 1 too. If I minus j equals 1, if a to the power of 1, so I minus j equals 1, a to the power of 1 will be equal to the identity. Okay, and this is not true, so I minus j has to be greater than 1, right? So I minus j in our case was 5 and 2, right? So 5 and 5 minus 2 would be 3, so this one will be 3, okay? So this one will be 3. 3 minus 1, 2, so you are here again, 2, okay? product by a, you're getting a to the power of 3, okay? And a to the power of 3 is the identity, okay? So a to the power of I minus j equals, it's the same as this, okay? And in our particular case, we were talking about a3, the next one after a2, okay? And that's the identity. Now that we are here, I can left multiply by the inverse, okay? So this a will disappear, right? And we will have a inverse on this side. So that's what we have here, okay? A to the power of I minus j minus 1 equals a to the inverse of a. And I minus j minus 1 has to be bigger than 1. Check, for instance, it cannot be 0. I minus j minus 1 cannot be 0, because if that happens, this one I minus j would be equal to 1. If I minus j equal 1, I minus j equal 1 means that a equals the identity. Not possible. We are out of that. That will also prove that that is a group, okay, but that is checked, okay, a subgroup, sorry, okay. So this, we cannot have a 0 here, okay. So since we checked that I minus j minus 1 cannot equal 0, if that happens, that was the first case that we already took out, okay. So the minimum value here is 1, right? Okay. And now it can be 1, it can be 2, it can be 3. It depends when the element repeats itself here, okay? So since a to the power of I minus j minus 1, this one, I minus j minus 1 equals the inverse, okay, so the inverse, we proved that since the inverse is in j, so this is the same as saying the inverse is in h, not in j, in h. The inverse is in h, so h is a subgroup of G, okay. So H is a subgroup of G if H is closed under the operation of G, okay. And this concludes the proof.